Hello everyone. So today we are going to talk about how computers understand whatever we ask computer to do. Now so far we have been looking into the ISA extensively. We understand the difference between, or we try to understand the difference between ISA and the microarchitecture through an analogy. Now we are slightly taking a detour from the discussion on ISA, and before we move further we would like to understand how a computer basically uh, interprets the kind of instructions we give. Now as we know that computers are not are unable to understand the way we talk or the languages we use for communication. So they need to be told slightly in a different way, and also whatever we need to tell them, it has to be encoded in some form which the computer can understand. And what is this form? This form is called the language of bits. So to be more precise, computers understand only binary language. So basically, as all of you have been exposed to, and I am sure all of you have understood or studied about binary number systems in your +2 as well as in the first semester courses like digital circuits. So I will not be going into too much details of the things which you have already seen. So I know, like, you guys have seen that binary digits are basically zeros, 0 and 1. So everything you want to express, you need to express through these zeros and ones. You also have I am sure you also know that 8 bits are called bytes. Now this is for simplicity of representation, and it is nothing sacrosanct. Like IBM in their first IBM 360 processor, they said that okay, they need to represent this 8 bit multiple times. So they said that okay, can we call this collection of 8 bits as byte, and that's how it started, and it has been continuing. Then I'm sure you guys also know about kilobytes. So basically 2 to the power 10 is represented at 1 kilobyte. Similarly megabytes and so on. So these things you already know. You also know the logical operations, for example AND, NAND, NOR, how you can use these binary numbers for implementing logic, etc. All right. And I am also quite sure that you guys remember the De Morgan's theorem and the other related things. So how you can minimize a Boolean expression, etc., using De Morgan's theorem. So all these things you must be remembering. If you need to recap some of these things, feel free to look into the textbook, the second chapter of the textbook. Continuing from there, you guys also mostly have dealt with so far positive binary numbers. So actually any number you in binary you have dealt with, mostly they were positive numbers, and I hope simple addition of positive numbers, etc., should not be an issue for any of you. You can also very quickly by looking at a binary number can tell what will be the equivalent of that number in decimal number system. Now decimal number system we are most familiar with, and you also might have basically known the reasons of decimal number system becoming so popular It's it is basically assumed that since we all have 10 fingers, that's why the decimal number system, where every number is represented with 10 digits, became so popular. Now, on the contrary, binary number system uses only two numbers, ones and zeros, to represent all the other numbers. Now, one very natural question can be why our computers were also not designed in such a way that it can work on decimal number system. It is very much possible, right? Because we can just have different symbols for these numbers 1 to basically 0 to 9, and the computer can understand those different symbols and work on them. Now, the reason why this was not done is again coming from the basically the constraints the technology provides. So, what are the constraints that possibly control the number of digits we should deal with? So, let me give you a very simple and brief explanation for that. And so let us say we know that in our computers all these different values are represented by some level of voltage. So, if your computer is working on let us say a voltage range of 0 to 5 volt, all right. So, basically 0 is your ground and 5 volt is your VDD. So, VDD is the highest voltage and this is the ground voltage in your circuit, because remember that underneath your computer there is a circuit, right, and that circuit needs to operate, and that how it operates using this different voltage levels. Okay. So, it operates using these different voltage levels. So, 0 represents ground, 5 volt represents VDD. Now, if I have a number system which has, let us say, 10 symbols, then what I will do, I will divide this range of voltage into let me just focus this. Okay. So, I will now divide this whole range into, if I have 10 symbols, then I have to divide this whole range into 10 different symbols. So, how can I divide that? So, if I divide this range into 10 symbols, then basically I will have let us say 0 volt corresponding to the number 0, then 0.5 volt corresponding to the number 1, then 1 volt corresponding to 2, and so on. So, basically 5 volt will correspond to the number 9. Now, think about a situation. So, I have a computer. Now, in this computer, if the voltage level is 0 volt, then I will know that okay, this is the number which is getting represented. If this is the voltage, then I know that this is the voltage that needs to be represented. Now, this is fine, it can be done. I can have a kind of a voltage detector which detects whether the input voltage is 0 volt or 0.5 volt and so on, and accordingly it can tell me what is the voltage, what is the number I am trying to communicate. But here the gap between two numbers is 0.5 volt, right. So, that is significantly small compared to, let us say, if I only represent this to basically this, or if I divide this voltage range into 2 digits. So, basically 0 represents 0 volt, the number 0, and 5 volt represents 1. So, basically if it is if I am my input is 0 volt, then I will assume that or I will take that as the binary digit 0, and if it is 5 volt, then the number I will take is as 1. So, in this case the advantage is I have a huge noise margin. So, this is called noise margin. What is the use of this noise margin? So, for example, let us say I was communicating. So, from sensor the data was getting communicated to the chip, and in between there is some, let us say, noisy environment where the voltage was fluctuating and so on. But still, if this kind of voltage level is maintained, then it is very unlikely that a 0 will be converted to 1 or a 1 will be converted to 0. So, basically noise, the amount of noise I will need to flip one bit which is 0 to 1 in this case is much more. But in this case you see that a noise of 0.5 volt can change my bit values, change my basically the value which I am taking as input. So, here the noise margin is pretty small compared to this case. So, because of this the binary number system has been accepted for all computing purposes. I hope that makes sense. There are many other reasons, and I am just very briefly introducing you about this noise concept. But going forward, when some of you will take other courses on especially communication etc., this concept will become very relevant. All right. And the basic other things like in any number system there is this numbers will have their positional value. So, for example, if I write down the number 530, so which is nothing but this is our hundreds position, this is tens and this is ones. So, you know that 500 plus 3 plus 0. Similarly, if I represent a number in binary system which is, let us say, 1101, so this means 2 to the power 4, which is basically yeah. So, this is 1 plus your 4 plus 8. So, this is 2 to the power 3. So, so that is how you know that this number is 13. All right. So, these things I am not going going to repeat. So, I hope all of you are familiar and comfortable with this. There are a few other number systems like hexadecimal and octal number systems, where basically in hexadecimal instead of 10 numbers you have 16 numbers to deal with. So, these numbers are represented as 0 to 9, then A, B, C, D, E and F and they are represented as 0, basically starts with 0x, and hexadecimal has its own several advantages. So, it becomes much more readable for humans in the hexadecimal number system compared to a binary number system. Similarly, the octal number system basically starts from 0 and goes till 7, and with this you represent all the numbers which you want to represent. And of course, the number systems will have their MSBs and LSBs. So, basically this is your MSB, this is your LSB. So, these are very standard things which all of you I am sure are familiar with. So, this was just a very brief recap of what you already know. Now, the things which we will be spending more time on is basically how to represent negative numbers in binary. All right. Okay. So basically we will start with negative integers. All right. So how do we represent negative numbers or negative integers in binary? So far we have only dealt with unsigned binary numbers. So we unsigned binary numbers which were always positive. So if we want to represent a number, let's say as in 4 bits or 5 bits, so we will just represent the number in their ones and zeros in those 4 or 5 bits, whatever we choose to. But when we talk about negative integers and their representation, so basically we need some kind of a mapping now. So we know that if I have n bits to represent a binary number, for example, let us say I have 4 bits to represent a binary number. So I know that I have in my disposal the numbers starting from 0000 till all ones, all 4 ones. So this is the set of numbers I have in 4 bits. Now if I want to represent, let us say using 4 bits, negative numbers or negative integers as well. So what I have to do? Essentially I have to find out some kind of a mapping. So what that mapping says? The mapping says that among these numbers I will use some of these numbers for mapping the negative numbers which can be represented using 4 bits, and rest of them will be used for representing the positive numbers. So this is, let us say this is the whole set of numbers which I can represent using 4 bits, and so far we have not dealt with any negative numbers. So let us say we call them the set of numbers which are all positive numbers, and what I have a set of positive and negative numbers. So I have this set now, and I have to find a mapping. So I have to find a mapping which will map this set of positive and negative numbers to a set of basically positive numbers, because so far we have only known about positive numbers. So if we take this example, so with 4 bits I have this set of positive numbers. Now I have a set of positive and negative numbers. I have to find out a mapping between this positive and negative numbers with this set of only positive numbers. All right. So what are the ways we can do that, and what are the things we should be careful about while we do this numbering? So one thing we should be very careful about while we plan to do this mapping is that there should be a unique mapping. It should not happen that let us say -3 is mapped with in this set of positive numbers with multiple numbers. So let us say one mapping can be this. So I will come to like how do we do this mapping, but let's just for simplicity we now assume that this is one mapping for -3, but -3 should not have any other mapping in this number in this set of numbers. Number 3 should have a one-on-one mapping between these two sets. So, basically the properties of this mapping should be such that there is basically one-on-one mapping or one-to-one mapping. So, there should be a one-to-one mapping. Then this mapping should be also complete. So, basically all the numbers which are there here in this set, they should be mapped here or mapped to this set of positive numbers. So, basically all entries should be mapped. So, basically all entries should be mapped. All entries in this, let us say we call this set S. So, all entries in S should be mapped. The other very important thing is we should not be just do the mapping mapping somehow and forget about it, because what is the purpose of the whole purpose of representing these numbers? We want to do arithmetic operations. So, the mapping should be such that we can do the arithmetic operations easily. So, basically we should be able to perform different arithmetic operations like addition, subtraction easily. So, basically should be easy to perform addition, subtraction, this kind of operation. And we should also look for the simplest way of doing it, right? Because we should not make things very complicated, then it is not going to serve the purpose. Now, one way of doing this mapping could be introducing something called a sign bit. So, let us say we have an n bit number system. It's best to understand through some example. So, let us say in this example n is 3. So, what do we so basically we have a 3 bit number system. So, the numbers are from 0 0 0 to 1 1 1. These are our numbers, all right. Now, what is the so one simple way of representing these numbers, representing negative numbers, could be introduction of a sign bit. So, what does that mean? It says that okay, the most significant bit is reserved for denoting sign of the number, all right. So, if the most significant bit of the number is 0, then we will say that okay, this is a positive number, and if the most significant bit is 1, then we will call it a negative number. So, we can write it down through some expression like this. So, we can write it down as, let us say this is sign bit. Sign bit of a number u will be 1 if this number u is less than 0, and it will be 0 if the number is greater than 0, all right. So, this is a theoretical basically this is one way of representing that how we can define a sign bit. So, just take some examples. So, it's very easy. So, let us say we have this okay. So, let us say we have a 4-bit number system. So, in 4-bit number system, the number 5 will be represented as, so we are talking about 4-bit number system, alright. So, the number 5 will be represented as, so 0 1 0 1. So, basically this is 1 and this is 4. So, 1 plus 4 gives us 4 and the sign bit here is 0. So, that is indicating that it is a positive 5. Now, how can we represent negative 5? So, in this sign magnitude representation, so this is called basically sign magnitude representation. So, minus 5 can be represented very easily just by we keep the actual number same, only flip the sign bit. So, the flip sign bit will become 1 and the rest of the number remains same. This is how you represent minus 5. You can take another example, let us say minus 3. So, 3 how will you represent? 3 will be 1 1 0 0. So, since it is minus 3, so this most significant bit will be basically, this will be not 0, it will be 1. So, the representation, so let me write it down completely. So, the representation will be 1 0 1 1. So, that is the representation for 3. I hope this makes sense. So, if we come back to this more formal representation, so any number in this sign magnitude representation will be basically represented by like this. So, you will have a sign bit, so you will have a sign bit and then the basically mod of the number. So, just remove the negative sign and whatever is the absolute value you represent it in that many bits, alright. Now, do you see any problem with this kind of representation of number? Okay. So, the problems in this kind of representation of a number is that you see how we will represent 0. So, 0 can be represented. So, again we are sticking to this 4-bit number system. So, 4-bit number system. So, 0 can be represented by 0. So, this is a positive 0. I can represent 0 as this as well, because these are valid representations, right. So, this is a negative 0. So, basically we have two representations for 0. So, this violates that there will be one-on-one mapping for all the numbers. Now, you have 0 mapped to this set of numbers in not a one-on-one kind of setup. If you look further, the arithmetic operations, basically addition, subtraction, that will also create problem. For example, let us say take the number minus 3, so which is represented as 1 0 1 1, and let us say plus 5, which is represented as 0 1 0 1, all right. Now, if I do addition between these two numbers, we know that minus 3 plus 5 should give us plus 2. Now, if you do the addition, you will see that 1 plus 1 is 1 0. So, we have 0 here, we have a carry here. So, again 1 plus 1 gives us 0, we have again carry and so on. So, again we got a carry. So, you see the result is there is an overflow, but even if we do not consider that, the result is not correct, right. So, basically this number system where we only introduce a sign bit and represent the number as it is not going to work. So, but the thing which we can learn from this number system or this way of representing numbers is that the concept of this sign bit. So, we are saying that okay, basically the takeaway point from this sign representation, sign magnitude representation is the concept of sign bit. So, we can use the MSB for representing the sign of the number. Now, if we take this concept further and we try to build or we try to find out the mapping function. So, remember that the whole objective we started with is we need a mapping function which can map the positive and negative numbers to a set of positive numbers in such a way so that we can do all the arithmetic operations or all the things we want to do with the numbers efficiently. Now, with this objective, if we further go ahead and we look at what is called ones complement. Now, this ones complement, again I am sure many of you might have already seen this ones complement representation. So, what this ones complement representation says? So, we will start with an examples. So, examples of a 4-bit number system where we represent them in ones complement. All right. So, how is, so let us say this is our positive 3. So, in 4-bit number system positive 3 will be represented as 0 0 1 1. Now, what ones complement says that how we will represent minus 3? So, it says that you flip all the bits, which were basically the way you represent a positive 3. If you flip all the bits, then you will get your negative 3. So, it means that 1 1 0 0. Similarly, 5, if you 5 in 4-bit number system will be represented as this positive 5, and minus 5 will be just make all ones basically zeros to 1 and ones to 0. All right. So, basically when we say flip the number of bits in binary number system, so I just want to highlight this point. So, let us say I have a number x in binary. So, by flipping we mean x bar, right. So, if x is 1, x bar is 0. Similarly, if x is 0, x bar is 1. Fine. So, that is what we mean by flipping. Now, there is something more interesting to also to look at. Now, the what we can say that x bar is nothing but 1 minus x. So, what is 1 minus x? So, if I have 1 here, so 1 minus x will be 1 minus 1, which is also 0. Similarly, if I have 0 here, 1 minus 0 will be 1. So, here the observation which we are trying to highlight is that flipping is same as basically subtracting it from the highest possible number that you can represent with that many bits. So, if I say that this is your positive 3 and by flipping you get negative 3, I can also equivalently say that I can achieve to this negative 3 by, so this is the highest number I can write using 4 bits, by subtracting my positive 3 from this highest number. So, I will get the same number what I got by flipping. So, basically 1 minus 1 0, 1 minus 1 0 and 1 minus 0 is 1, 1 minus 0 is 1. So, what I am trying to say is basically for simple basically operational ease, we can say that okay, you flip the bit to get 1's complement, but the other way of achieving it is basically 2 to the power n minus 1 2 to the power n minus 1 minus the positive number will also give you the same result as flipping all the bits. So, if we write down it formally, so basically in 1's complement a number u is represented like this. If the number is greater than 0, if u is greater than 0, then it is the representation of the number u using that number of bits, the positive representation. And if the number is negative, then what you will do? You can either take the complement of the number, basically you flip all the bits, or you can achieve the same result by doing this. You find out the basically the highest number which you can represent using those number of bits, which is 2 to the power n minus 1 minus the absolute value of that number. So, this is what your 1's complement is. All right. Now, I am sure all of you have understood how I can represent a number in its 1's complement form, but does it basically satisfy all the other requirements which we started with, that the number has to be uniquely represent, basically the mapping function has to be unique, or one-on-one mapping should be there, and the arithmetic operations should be easy to do, and so on. Now, in 1's complement system, if you see the number 0, so the number 0 is represented like this. How about, is there any other representation of 0? Yes, there is. I can also represent 0 like this, because again I am flipping the number, flipping all the bits, and still I will be representing 0 only. So, again I have 2 representations for 0, which is a problem. Using this ones complement number system, you can easily do addition of positive numbers. For example, if I want to add, let us say 3 with 5 or let us say 3 with 2, then it is very easy if I am dealing with positive numbers. So, basically you get the appropriate result. So, basically this is 3, this is 2, and you get your result as 5. So, that is fine. But what happens when you want to add negative numbers, or basically you want to deal with negative numbers? So, take an example. Let us say I want to add 3 with negative 2. So, we know the answer. We should get plus 1 as the result. So, let us see whether we can get that. So, 3 positive 3 is 0 0 1 1. How we will represent the negative 2? So, this is positive 2. So, we have to flip all the bits. So, basically 1 1 0 1. So, that is your negative 2. Now, if I just add them, so basically you get this as answer, which is not your positive 1. So, definitely there is something more need to be done, because this is not helping us in doing the arithmetic operations very conveniently, or it requires more effort to get the arithmetic operations done. All right. Though both these representations which we have looked at so far, one was basically having a having MSB as sign bit, another is this ones complement numbering system. They have their flaws, but they introduce to some interesting ideas. One talks about having a sign bit, and the other one talks about complement. So, basically this ones complement method. So, basically this idea of complement and idea of sign bit, they we can exploit these ideas and try to build on those to form an idea which can help us in answering all these challenges which has been discussed so far. All right. So, there are other approaches like which are called bias based approaches, where any number is represented as that number plus some bias. So, for example, let us say consider a 4-bit number system with bias which is equal to 7. So, basically 4-bit number system with bias value of 7. So, what does that mean? That means that the number, let us say minus 3. So, minus 3 will be represented as the number plus the bias, which is 7 in this case. So, basically which is 4. So, if I want to represent this number in our 4-bit number system, then we will write down the binary representation of 4. So, 0 1 0 0. All right. Similarly, plus 3 if I want to represent, so that will be basically 3 plus 7, which is 10. And how do we represent 10? So, 10 will be 0 1, so 2 and 0 1. So, 8 plus 2. So, that is how you get 10, right. So, basically 2 to the power 3 and 2 to the power 1. I hope all of you are you are very much comfortable with this thing now. So, with the bias system, you have some advantages, especially with your arithmetic operations like addition, etc. This becomes easier to do, but multiplication remains very difficult to implement. So, we will use all these three concepts. So, the concepts which we have seen in these different number systems are basically the bias, addition of bias, then this complementing numbers in one's complement, and then introduction of sign bit. These are the different concepts we have seen so far. Now, all of them has their difficulties, or all of them has their shortcomings. So, we will try to address those shortcomings using a different or basically by finding some solution to that. Now, one concept which is very useful to understand how we can do this mapping efficiently is called number circle. So, number circle. So, what it says is that you write down all the numbers which you can represent using those limited number of bits and write them in a circular form. So, for example, let us say I have I have only 2 bits to deal with. So, what are the numbers I can write down? I can write down 0 0, 0 1, then I can write down 1 0 and 1 1. So, what it says that you write the numbers on a circle, and now since you are going in this circular form, so basically you start with 0 1 2 3, right. Now, after 3 in the circle there is a break, right. After 3, if you go in this circular fashion, you will be reaching to 0. Now, whenever you go clockwise, you basically increment your number. So, basically if you from 0 0 to 0 1 you go clockwise, then you are incrementing the number, and if you go in the reverse direction, that means anti-clockwise, your numbers decrease, you decrement the numbers. Only thing is there is a break point here at when you jump from 1 1 to 0 0. So, this is the number representation when you have only positive numbers. Now, from taking cue from this, can we write down a number circle which looks like this, and here I will write down a little bigger number circle for let us say 4-bit numbers. So, for 4-bit we start with 0 0 0 0, then we go to 0 1 1. All right. So, this is 5 6 so basically 0 1 2 3 4 5 7. Now, the next number is 1 0 0. Now, you remember that the concept of sign bit. So, if we apply that same concept of sign bit here, so you see that here all the numbers had 0 in their MSB, so they were positive numbers, so 0 to 7. But when we move to this next number 1000, the sign bit has changed. So now if we borrow the concept of sign bit, then this is a negative number. So just let's continue with this numbering system, and let's call this number, or let's say that this number is minus 8. So this is our negative number, and it is representing minus 8. Similarly, if we go further, the next number is 1001, and we call it minus 7. So the next number is basically 1010, and we call it minus 6. Then 1011, which is minus 5. Next number is 1100, which is minus 4. 1101 minus 3. 1110 minus 2, and finally all ones, which is minus 1. So what we are saying? We are saying that we are drawing a number circle. So this is our circle. All right. So if you see, if I go clockwise, the number is always incrementing. So whether we are in the positive part or negative part, so it starts from 000 to 7, and then if I increment further, there is a break. So basically from this number to this number, there is a jump. So this is we call break point. All right. So what are the advantages, or why we are representing the numbers like this? So here we have used the concept of sign magnitude, and here you see that another advantage is 0 is represented by one number only, and if you go anti-clockwise, you decrement the number. So in this number circle, the advantage is, like if you want to add a number m to a number n, so what you have to do? You have to locate either of these numbers. Let's say we locate the number n. So let's take some examples. So let's say n is 2, m is 5. So we locate the number 2, and then we need to add 5. So we need to go clockwise 5 steps. All right. So basically this is where we are. So 1, 2, 3, 4 and 5. So basically our result is plus 7. So which is what is expected. Now if this number is negative, let's say we need to add 5 and negative 2. So what we need to do? We need to now go anti-clockwise. So 5 is there, so we can locate 5 in the number circle, and since the number is minus 2, so we need to go anti-clockwise 2 steps to reach the answer. So basically if we go anti-clockwise, so from 5 we will reach 1, 2, so basically 3 is the answer. So far so good. All right. So this is one way, that if the number is negative, you go anti-clockwise. If the number is positive, if you go clockwise. There is another way of looking into it. going anti-clockwise from here 2 steps is equivalent to going this many steps in clockwise direction. So, this is very, very important. So, what we are saying that from here we can go, if the number I am trying to add is negative, then we can go in the negative direction these 2 steps. The equivalent to this, because we are talking about a number circle, is moving these many steps clockwise. So, and what is that number? This number is nothing but 2 to the power n minus the number of steps which we are supposed to go. So, basically in this case n, right. So, what it says? It says that if the number you want to subtract, you can basically locate the positive number, you can go anti-clockwise that many steps to find out the answer, or you can go from here in the clockwise direction, but the number of steps you need to take is 2 to the power n minus this capital N. So, here we are talking about 4-bit representation. So, what is 2 to the power n? So, 2 to the power n is 16. Right. So, 2 to the power n is 16 here. 16 minus 2 is equal to 14. So, if I go 14 steps in the clockwise direction, so basically 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So, that is my answer. So, you either go anti-clockwise or you go clockwise. Now, if you have a number which is let us say I want to add 5 plus 3. So, I am at 5 here. Now, if you add 3, now you will be reaching or you will be crossing this break point, and that will create an overflow. So, we will talk about overflow in a little bit later and how to deal with overflow in our later part. So, this actually will form the base for our discussion on 2's complement representation. So, we will pause here for a moment for any questions, and then from here we will move to the 2's complement representation. So, please feel free to ask your questions. Thank you.